Yeah, so hello everyone, I'm Anna and I'm going to present on supporting Bayesian modeling workflow with iterative filtering for multiverse analysis. So when we say supporting Bayesian modeling workflows, what we care about in this project is specifically how to support iterative model building. Because in many applied fields, like for example ecology, medicine, psychology, economics, we care about data-informed decision-making or policy shaping. And it's quite common to build models iteratively. It can be intuitive to look at multiple candidate models, but it's not necessarily transparent, this process. And also we don't necessarily know that we have sufficiently explored the space of possible models. So what we require to be able to use statistical and specifically Bayesian modeling in all of those fields is of course a degree of transparency, because we want to ensure reproducibility and robustness, and we cannot do that without a transparent modeling procedure. We also want reliable estimates, and of course we want uncertainty quantification. This comes with challenges. So of course we always have limited resources, limited time, limited computational resources, also limited modeling ideas. And then of course in the context of Bayesian modeling workflow, it's most important to say that there are many intertwined tasks. So the model builder also needs to check computation, and the person implementing an algorithm also needs to think about the modeling side. So we have to navigate a lot of necessary and also optional steps throughout the modeling workflow. And how can we do this? How can we support modelers in this? So what we are looking into is actually, an approach that helps us at least with some of those challenges. And so as opposed to a traditional analysis where we look at some models and then we report one, or a pre-registered analysis where we look at one model that we then also report, we are now looking at multiverse analysis, which is an approach where we think about plausible or possible modeling choices for a problem at hand, and then we create a combination of models just based on those defensible modeling choices. So what does this help us with the previous challenges? So now we get transparent communication of modeling choices. This is great. We also explore model space a bit faster, because we don't start with one model and then look at the next model, but we start with a chunk of models. So this is also nice for this iterative nature of model building. And third point is that we can actually, with multiverse analysis, elicit a set of plausible models from a modeler, because we usually in applications don't have access to the full space of models. So multiverse analysis is in a way an informal prior that we elicit from the modeler about which models are a priori possible and plausible candidates. So this is how this looks like for an example of analyzing effect of treatment. So here the quantity of interest is the posterior results for treatment. We are, like for simplicity, just looking at the coefficient for treatment, and we have 24 different models. And those models differ depending on the distributional families for observations and priors that were chosen, included covariates and also something like interaction effects. But there could be more modeling choices, like for example looking at varying effects on different hierarchical levels in the data. So what we see is that there is a range of possible conclusions. So some of those models clearly indicate a negative sign of this coefficient, which in this example means a positive effect of the treatment. So we are reducing the adverse outcome for the patient. Other models don't allow us to make this conclusion. There's much more uncertainty in the posterior for the coefficient for treatment. So it's great. We see multiple models are possible. This is more transparent than if we would have started with any one of those. We also see that there are differences in conclusions, so this should help us with reporting a more reproducible analysis. But then we don't know from this plot which of those models are the more promising candidates, which of those models adhere to criteria of model quality that we care about. And so this is what this talk and this work is about. We want to combine multiverse analysis with recommendations from Bayesian workflow to evaluate and, in the end, filter such sets of models towards models, fewer models of higher quality. And this is our proposed approach. So it's important to note that this is a high-level approach. Not at any point are we saying you have to use one specific metric to do this, because of course, as in all workflow considerations, this is dependent on the modeling problem itself. But what we are suggesting is to start with filtering by predictive abilities, because this is related to how useful our model is going to be if we think about usefulness in the context of a model being usable for future unseen data. And then secondly, we include a loop of changing and checking where we do computational checks and iteratively improve models. And we end the whole thing by filtering again by predictive performance or by predictive abilities. So this is, in short, how we propose to get from a set, like a large set of models where we have some models here in gray without computational issues and some models with computational issues, which are here red dashed lines, to a model where we have, to a set of models where we have validated our models and we can easier work with this filtered set of models. So what could examples be for filtering by predictive abilities? We are looking into, for example, visual posterior predictive checks. We are also looking at differences in estimates for expected log predictive densities, and then also checking the validity of the normal approximation in this context. But as I said, this approach does not dictate to use those. You can also use other criteria that help you evaluate predictive abilities. So how does this look like in our example? So we had the 24 models. We are now assessing differences in ELPD. And we see here in the triangles denote negative binomial models because we have count data in this specific example, and the circles are Poisson models. And we see that all of the Poisson models in this case have a computational issue, which is that the ELPD estimates are not reliable. So we have too high Pareto k-hat values. So we are basically, if we go back to here, we are basically in the upper part now, and we are seeing that some models have computational issues, other models are fine. So what do we do to get to the right-hand side? We are actually looking at visual posterior predictive checks for, well, basically the models are the same, just the distributional family for the observation differs. So we do those pairwise comparisons. Okay, I'm clicking wildly. But we just do those pairwise comparisons, and we can see that overall, all Poisson models are clearly worse at capturing relevant aspects of the data that we care about than all negative binomial models. So in this specific example, given this initial set of models, we can actually safely exclude the Poisson models from further consideration. Of course, this is dependent on the set of models that we start with. So if we actually would have then obtained models that are sufficiently good at predicting, but they still have computational issues, then we can enter this loop of changing and checking. So what do we mean by that? This could, for example, mean convergence checks, checks for efficiency, reliability, and iterative improvement. So the changing part, this is where we would maybe modify our model, modify the computation, or decide to extend a model. But again, many different possibilities. We are just trying to give a high-level framework how to connect all of those tasks. If you are interested in more examples on this, there's more in our preprint, and I can also talk about this more later, how this would look like if we have computational issues at this point and what you can do to improve them. We have an example for alternative ways of estimating ELPD and also for reparametrization in the preprint. So yeah, again, I think I already mentioned this a bit, so I'm going to be a bit quick here, but this is just some examples. Again, it depends what kind of methods are you using, also will dictate what kind of metrics you should use to evaluate them. But here are some examples. If you're, for example, using MCMC or HMC nuts, then there are different tools that we know to evaluate, for example, insufficient exploration of the posterior. Yeah, I'm going to leave this like that for now. So back to the example, we had all of those models. We saw a range of conclusions. We can apply the filtering, and we end up with a smaller set of models. So here we move from 24 models to 7 models, and we can see that actually those differences that we saw before, they vanish. So we have validated the set of models. We are left with only negative binomial models. In this case, they all show negative sign, roughly similar range, but also all show overlap with 0. So likely we would conclude that given those models and given the data, we cannot really draw any strong conclusions about the effect of treatment here. So to summarize, how can iterative filtering support the modeler? So first, we get more transparency without overwhelm in a way, because we have a tool here to validate models in a multiverse of models. We can transparently reduce sets of models, and we can move towards the more promising candidates while still remaining transparent. And secondly, we want to move from an implicit practice to more explicit frameworks. So we want to look at different subtasks in the modeling workflow, and specifically the connections between model building and computation checking. And how can we support modelers by actually giving them a clearer walkthrough on how to approach basically the different subtasks jointly. Then secondly, this approach also indicates decision points in the workflow. So maybe if you know Andrew Gelman and Aki Vehtari's paper on Bayesian workflow, and also other co-authors, many co-authors, then you might remember that at some point maybe you want to give up on a model. So in our case, we gave up on the Poisson models in this example. So we can use iterative filtering to indicate those decision points in the modeling workflow to some extent. Yeah, so this is just a quick summary. Iterative filtering is nice because you get an increase in transparency without overwhelm, and you can actually move from large sets of candidates to models that adhere to criteria of model quality that you care about. And yeah, our main assumptions here are that this space of all models is inaccessible, and it's not possible to form a meaningful prior over the models. And then also we assume for checking the predictions so that it actually is valid, we have to assume that we are working with causally sensible models, because otherwise we might run into issues there. And just lastly, we are assuming that we're not only interested in predictions, but we are also interested in certain quantities of interest and the posterior results for those. There's a preprint available on arXiv, and feel free to reach out and also, yeah, like reach out now, and I'm happy to take any questions. Yeah, thanks. Yeah.
Partition those models from those in the competing DAG. You don't like include a quieter in the prediction set, for example. So I wonder if you thought about that, like how, yeah, a principled way to sort of partition the sets of competing models. You don't have these inappropriately compared models on prediction.
Yeah. I mean, it's a very good point, and I think it's also, of course, for this project, we kind of maybe picked the easy way of saying, okay, let's just not worry about this right now. But it's true that, well, it's also not the same thing to check a statistical model versus to check a causal model. So it's indeed, I think, a very important but also very difficult question. How would we include such a check, for example, in a filtering tool? So if we would say, okay, let's drop the assumption of causally sensible models, how would we have some kind of check for that? I don't have an answer for that. But about the multiverse of multiverse, so multiverses, so there's some work also from, now I think Bell et al., if I remember correctly. So that's about multiverse analysis in machine learning. And there's also basically in the conclusions, they also have this comment that, of course, you could think about maybe in the spirit of multi-analyst studies as well, that you could start from different points in the modeling space. So kind of what this is just some appendix slide, but basically the idea that of course, there is this non-representativeness in the multiverse. And I think how I'm thinking about it for the sake of this project is more in the way that I was trying to explain with eliciting from this inaccessible space of models. So it is, in a way, subjective, if you will. So it's a way of taking information that the given modeler deems relevant in that sense. So I think this is a way to think about it I found useful. But of course, that doesn't solve the problem of checking for causal validity. Yeah. Sorry, I don't see who was first, but yeah.
Your
Hi.
work on modeling decision support is really interesting, and I have three heuristic questions. First is, do you have any lower threshold in how many models should be left in the end? Like for instance, 5 fits nicely into 1+, so
Yeah, that's a good question.
And second question is, how many models then should you start from compared to that number? Like, do you have 20 rules, so you should have at least like 25 models to start from? And third question is, when do you know how to increase the diversity of the model? I don't think it is like keep decreasing the diversity. Sometimes you realize, oh, we are somewhat constrained in a very small part of the model workflow, so
Yeah.
maybe you want to increase.
Yeah. Okay, I'm trying to keep track of the questions, but basically, so we don't have something like a threshold, so neither for the set of models that you should start with, nor with the set of models that you end up with, because we are working under the assumption that we just take basically a set of modeling choices that the modeler decides on. And then this dictates, like the combinatorics of that basically dictates the set of models that you start with. And then the filtering is not aiming, so it's not in a sense model selection in that we are aiming to select the best models. We are really removing models that are clearly worse. So while this might sound like it's the same thing, it's important to distinguish, I think. And then maybe just quickly to the last point. So this is what happens if so in our first initial example, we were ignoring that there's actually hierarchical structure in this specific data set. So there's patients and visits to the hospital. And if you include all of that, then suddenly you move from 24 models or 7 models that you were left with to a set of 192 or something models. And then, of course, the filtering will also, remove less. So, but the conclusions stay the same here, that we, of course, would just want to have more data to actually say something about the effect of treatment. But iterative filtering does not, the approach that we suggest, it does not hinder you to basically say, okay, now I filtered, but actually those models were likely too simple. What if I increase the complexity and then I filter again? So you can just do that. Yeah, I hope this answered some of the questions, yeah.
Just to clarify, you're using the word filtering as filtering out the model, not
Yes.
kind of particle filtering.
No, yeah, yeah. Yeah, okay. Thank you.
So now we have a 30-minute break.
Yep.